This is Chapter 2 and our discussion of chemistry in regards to matter. And there's a number of vocabulary words that I do want you to learn through our study, and most of them are listed below, and by the time we are done you will have learned what most of those words mean. So we're going to talk about the particular nature of matter. So what is all matter made up of? And the simplest way to put it is that all matter has the basic unit of the atom. So everything is basically made up of individual atoms. The word atom was used by someone over 2,000 years ago. In fact, it was well before Jesus Christ was born. And he used the term atom not really knowing what that term meant. And so for thousands of years, scientists have often wondered really what an atom was and what the matter that we see all around us is made up of. So now I tell you that we know this, and the question is, how do we know that that's true? And so we're going to take a look at a couple of pictures from a PowerPoint presentation about a scanning tunneling microscope. This showed that atoms are actually for real, not just somebody's weird thinking. So these are pictures of a device called this is a picture of platinum atoms taken by a device called a scanning tunneling microscope. And so if you look, the area that my little pointer is tracing out in the shape of a hexagon, that was actually a platinum atom. Nickel atoms look a little bit different than the platinum atoms do. So they have this little tip that electrically traces the small little area above an atom. And you can see that nickel and platinum atoms are individual. They are arranged very methodically, and they make up the materials that we see that we call platinum and nickel. Now, there was a company that did this. This was done back, I believe, in the late 80s, early 90s, by the following company. And so if you can read that, IBM is the company that pulled it off, and on this nickel background, which is going to be this, sorry about that, this area back in here, they were able to individually manipulate the xenon atoms in the shape of their logo. And this is a big deal. This was kind of bragging rights on how capable IBM is. But they did this trying to show that they could actually see actual atoms. So how do we know that this is true? We can say that we have seen them, and seen you might want to put in parentheses because we did not see them with our own eyes, but we used an instrument. And we also have what would be called empirical evidence of these atoms. And we'll explain what some of that evidence is as we go along here. So for atoms in general, what are atoms? Are they all alike? And atoms are not all alike. They tend to be very unique. So when we think about atoms, what I want you to think about is that there are atoms of gold, and the symbol for gold is AU on the periodic table. And there are atoms of iron, and the symbol for iron is Fe. These are two of the types of atoms that have unusual symbols for their name, and there are many actually, but these are just two of them. And gold atoms are gold atoms. They are very different than iron atoms. They behave the same. And in total, there are about 118 different kinds of atoms. And these atoms are going to be found in the world, but only 91 atoms are actually naturally occurring. So in some way, man has been able to make atoms that don't exist in nature, and they actually last a very short time before they decompose into other things. So 91 atoms are naturally occurring in nature. Okay? So here is the periodic table, and if you look up here, you will see the hydrogen, and then hydrogen and helium over here, and the numbering system goes all the way up to 118. These are the elements. Now this periodic table is old enough that it doesn't show the numbers 110 through 118, but all of them have been discovered at this time, and we can talk about that when we interact personally next week. So what are elements that we mention constantly? Elements are substances that are made up of one kind of atom. So when I talk about a carbon atom, there's only one kind of carbon atom. And gold, likewise, silver, iron, all these different atoms are different one from another. And an element is only one kind of atom. Now there are some unique things that happen. You might say, wait, I thought I heard that diamond was also carbon, as is my pencil, quote-unquote, lead. Well, there are different forms of carbon. We call them allotropes. And allotropes are simply different physical forms of the same element. So your pencil lead, quote-unquote, is actually a form of carbon called graphite. And then you have something like coal, which is another form of carbon, or you are familiar with diamond, another form of carbon. And all of these are all carbon. They're just connected to each atom is connected differently to each other, and therefore we see different things. Okay? So atoms, I like to say, are like the alphabet, and let me make this comparison. Alphabet is the basic unit, and we use the letters of the alphabet to make words. Well, the basic unit for chemistry are the elements. So we have things like carbon and oxygen and hydrogen, and we can combine these in order to make other substances, and those other substances are called compounds. And compounds are two or more different atoms, and those atoms are chemically connected. And when I say that they are chemically connected, there's a technical name, and we say that they are bonded together. Okay? And we'll learn more about bonding as we go on in our study of chemistry, but not in this unit. So, some common substances that you might be familiar with. Something like carbon dioxide is a compound, and we write that as CO2, carbon dioxide. It is made up of two different kinds of atoms, and there are one carbon for every two oxygen. Water is made up of two different kinds of atoms. You have two hydrogen and one oxygen. And then if I want to get a little bit further in, I could say that we could make sugar. This is a form of sugar called glucose, which is 3 different kinds of atoms: carbon, hydrogen, and oxygen. And this type of sugar is used in photosynthesis along with water and carbon dioxide. So all of these are compounds. You might be familiar with another compound called sodium chloride, NaCl. This is common table salt. So all of these are compounds because they contain 2 or more different kinds of atoms. And we say that compounds have a constant composition. And what we mean by that is they always have the same types of atoms and they're always in the same ratio. So, when I think about water, water is always made up of 2 hydrogens and 1 oxygen. Sodium chloride, 1 sodium, 1 chlorine, and glucose is 6 carbons, 12 hydrogens, and 6 oxygens. This is what constant composition means. So if I have polluted water, that still contains just water. It doesn't contain water with a different formula. There are other things that are added to the water to make it polluted, but the water that is in polluted water is still H2O. Now there's a little tricky thing that I don't want you to get confused about, so I will tell you what that is right now. There are these things called diatomic molecules that are elements. They're not compounds. So, are diatomic molecules elements or compounds? They are elements. They are not compounds. So what are these diatomic elements? There are 7 of them that I want you to memorize because they are the most common. And they are H2, N2, O2, F2, CO2, Br2, and I2. So you will need to memorize these, and why this is important is because many of these are common. They're commonly used in chemical reactions that we will talk about, and every time that we talk about them, I want you to kind of see in your mind that when hydrogen occurs as an element, there are 2 atoms that come together. The same is going to be true for nitrogen or oxygen. So the oxygen and nitrogen in the air that you breathe is made up of 2 oxygens connected together, or the nitrogen is 2 nitrogens connected together, and our body breathes in these things. The oxygen we use, the nitrogen we don't use. But the oxygen is not just a single atom of oxygen, it's 2 atoms. And when we talk about bonding, we'll discover why there are 2 atoms for all of these diatomics. Now, let's look at a simple way to memorize these. One possible way is to use the periodic table. And if you go up to number 1, way up over here, you'll see the hydrogen atom, and then go to number 7. Nitrogen is right here, and I'm using the number on the top. You see that's hydrogen is 1 up on top, nitrogen is 7, and then 7, 8, 9, and now go down to those 4. So when I'm looking at the periodic table, what I'm actually seeing is a pattern that's going to help me to memorize the diatomic elements. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Notice that number 7, oxygen, fluorine, chlorine, bromine, iodine, make the shape of the number 7. So in all, there are 7 diatomic elements. hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. This gives us our diatomics that we need to memorize. Some students prefer to think of it as having met a man called Mr. Brinkelhoff. B-R-I-N-C-L-H-O-F. So that would be bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Mr. Brinkelhoff. So whatever way you want to use to memorize that, that's fine. So let's review real quickly the language of chemistry. The alphabet for the language of chemistry are the elements. The elements form the simplest unit, and we put elements together and we make compounds. And then compounds can actually be formed into what I would call sentences. And sentences in chemistry would be like a chemical equation. And a chemical equation tells me about something that I start with, and it reacts and becomes something new. So, for an example, let's make salt. Sodium plus chlorine. Well, chlorine we know is diatomic, so I always have to write Cl2, is going to make salt. Sodium chloride, NaCl. Now some of you may have heard how to balance equations, so I'm going to do that. I don't expect you to know how to do this at that point in time. But I notice that there are 2 chlorines here, but there's only 1 over here. So since I want to keep sodium chloride as the product, I put a 2 there, and I'll need 2 sodiums. That gives me 2 sodiums here, 2 chlorines there, and the arrow can be treated like an equal sign. I have 2 sodiums and 2 chlorines because the 2 distributes to both. And that's our introduction in Chapter 2.